Cool. So topic is algorithms. Who can tell me what an algorithm is? Just like regular language definition.
A set procedure to solve a problem.
Yep. That's it. That's all an algorithm is. Series of steps. So you could say that the algorithm for making a peanut butter and jelly sandwich is like, you take the bag of bread out and you open it up and you take the top piece out and you put it on the table. Then you take the peanut butter out and then you put that on the counter and then you open up the lid and then you take the, so like just a set of instructions. And the power of algorithms is if we can describe this as a set of steps that we do exactly the same every single time, now we're in the category of things that computers do super good. It's not interpretive. At no point do you need to, is it ever unclear what the next step is. So with that benefit, like we can make a computer do it so we don't have to do it ourselves. So that's abstractly what an algorithm is. In practice, you're going to see like two kinds of algorithms come up over and over again. So by the, come on, get over here. Screen sharing. There we go. Oh shoot, I lost my, that bums me out. I wrote a whole bunch of stuff on my whiteboard a second ago. Now it's not here anymore. All right, whatever. By the end of this lesson, I hope that each and every one of you will be able to explain how big O notation works, and I hope that you will be able to perform an insertion sort. If we have time, we'll talk about select sort also. The two types of algorithms that we're going to see over and over again are, come on, searches and sorts. So given a collection of things, can you put them in order? Cool. How? How can you describe it as a series of steps that works abstractly? What if you don't know that you have 1 through 10 on the cards? What if you don't know what the boundaries of the numbers are at all? What if there's gaps, you're missing numbers? How would you still have a set of instructions to sort something? So there's a whole bunch of different algorithms for this. There's one called bubble sort. There's, I told you we're going to talk about insertion sort. There's one called selection sort. There's merge sort. There's heap sort. And like, but the reason this entire topic is like, why it's not an official part of the curriculum at Flatiron, why it's mostly a Mod 6 thing, is that like, the correct answer is quicksort. There's like a specific algorithm that works most of the time in most kinds of situations where you need to sort something. It's already done. Mathematician figured it out. Just do that one. The reality is you are like, you have a non-zero chance that somebody's going to ask you about one of these fucking things in the job interview, because this is what they do in computer science school, is talk about this stuff. And so if somebody's expecting you to be a computer scientist, like this is the language you have to speak. Similarly, like really exact same thing with searching is we have a couple different algorithms that it's just worth being familiar with. So there's one called depth first search. There's another one called breadth first search. Couple different, and then we can search through like arrays, like just collection of things like our playing cards. You can also search things called graphs, which are a little bit more like how modern, like internet-y kind of stuff works. So there's a few of these things that are worth being familiar with, but they all like have they have the same goal and they have very familiar shapes to them. And your selection of one thing over another thing has a lot to do with this big O notation. You've probably heard about it. You're probably scared of it. You shouldn't be. This is like maybe the easiest thing in computer science to wrap your head around. Big O notation is a way to describe how something's complexity changes as it grows. And it looks like O, like a capital O. That's why it's called big O. And then parentheses. And then you describe how it changes as it grows. If I'm trying to, for example, do a sort, if it's O of n, that means that it takes the exact same, an amount of time proportional to how big the thing is. Cool. If it's O of n squared, that means for every new thing that you add in as an input to it, if the thing gets one bigger, it gets disproportionately harder to do the operation. So if it's a sort, for example, a lot of these sorts are O of n squared, because if you're comparing everything that you're sorting to basically every other thing in the list, that ends up being O of n squared. So as the list gets bigger, you not only have more things to sort, that would be O of n, but you also have more things to compare them to. That makes it O of n squared. Another way you can think of like this big O kind of idea is ultimately it's like kind of comes down to counting loops. So if I have a for loop and I go through everything on a list, and inside of that, I have another for loop, and I'm going through everything on the list again inside of that, O of n squared. Really just counting the loops. There's a few different common values for big O. And they look like this. So O of n, that's our linear. If we can do it in less time, if we can potentially not have to go through every single one of these. So for example, searching for something in a sorted list. If it's already sorted, you know it is, all you have to do is locate where it is in the sorted thing. You might be able to find that without going through every single one. How? How is that the case?
If it's already sorted, like say it's a phone book, I am not going to go through A through whatever if I know it's N.
Right. And even if you don't know which letters are in the alphabet, you pick one in the middle. Is it above that or below that? And so then you can just keep doing that, and each time you're cutting the stack in half. That's O of log n. If I have to go through basically everything, so like that, like a search, for example, if I'm trying to find something in this like order of cards, and I go through every single one, well, I'm going to find it or I'm not. It's not going to get worse than that. And so you could say like, all right, well, O of n is like your worst case scenario for just like looking up something in a list of things. But as you can see, there are worse ones too. And the worst it can get is n factorial. So this is everything times every other thing. So factorial is like 5 times 4 times 3 times 2 times 1. So your worst algorithms are like that. So this is actually highly relevant. This isn't just like a weird mathematical quirk. Why do you think that this knowing the big O of something matters quite a fucking bit?
Probably when you're tackling gigantic databases of information that you just want to grab a couple selections from.
Exactly. So your student projects, you're never going to run into a big O problem. All of the shit you do could be O of n factorial. If you're Google, if you're Facebook, if you're Netflix, and you're doing something that grows with the data set like that, hope you didn't build your business around that, because at some point that grows so quickly that it's like mathematically never going to be cost effective to do it once it hits some threshold. So you got to find ways to keep your complexity down. So another way to think about complexity is, I didn't mention whether we're talking about space or time, and it applies to both of them. So when I talk about space and time, what am I talking about with computers?
How long it takes versus the amount of memory it takes.
Exactly. How much processing power do you need to crank through this versus how much disk space does it take up? So good example, if I have some algorithm for like sorting these things that requires me to keep a separate, like a temp array. One of the sorts that we're going to talk about, selection sort, works that way. You're gradually building up a like a sorted array as you're going through it. Well, one way to do that would be to have like a temporary thing and then your original thing, and then you just copy stuff over to it. Okay, well, as like your list gets bigger, now you need twice as much space for like your temporary variables and stuff. Now, all that said, 99 times out of 100, if somebody's asking you about the big O of an algorithm, they're talking about its time complexity. And they're specifically talking about its worst case scenario. What is the slowest that this could possibly run? And that's kind of that. One more interesting note on big O is coefficients don't matter, constants don't matter. So you might like look at an algorithm and go, oh, well, so it's O of n squared, but this other one is 2n or 2n plus 1 or something like that. Doesn't matter. It doesn't have any impact on how it grows. And that's all we're interested in with big O. And so like one of the ways we get around this nested loop problem in functional programming is doing chains. So if you do a map and then a filter, that's O of 2n, but it's still fundamentally O of n. It's growing proportionally every time, even if like the curve kind of tips a little bit, versus going through everything and then going through everything again inside of it. No bueno. All right, that is big O, and that is how it works. Ask me some questions.
Do you tend to see that, you know, as you're improving your time complexity, you're sort of screwing your space complexity?
Yeah, there's a pretty natural trade-off between those two things.
Okay.
It's not like a law or anything, but a lot of the time you're trading one for the other. In fact, those like baller algorithms like quicksort and stuff, a lot of like the magic behind them is they figured out a way to improve the computational complexity without a massive hit to the space complexity.
How much danger would you say there is of falling into the worse end of big O kind of issues? Are most frameworks, do they have fail safes in place to be like, hey man, you're getting into...
Oh, no one will ever tell you.
Yeah.
Your big giveaway is loops inside of loops. That's an uh-oh. For the rest of it, like if you are ever on the job writing one of these algorithms by hand, like you're doing it wrong. Like these are solved problems. Just use somebody else's solution for this. And all of these have very known big O's. So, but when you're doing your own stuff, that's a thing to be sensitive about. And that's one of the dead giveaways. Do I have a loop inside of a loop? That's probably going to grow real fucking weird. And the trade-off for that is usually, can you do it as a chain? Can you go through the entire thing and then the entire thing and then the entire thing? Because O of 3n is only bigger than O of n squared for like a hot second. And that's fine. Other questions about how big O works? One other knowledge nugget I'll drop on you for big O. So it took me a long time to figure out, but it's a good shorthand. This is size. This is time complexity. So that's O of n. As the size gets bigger, time complexity goes up proportionally. We can change the slope on it, but it still grows at roughly the same kind of rate. Then we have like our exponential curves, and then we have our logarithmic curves. So going through every single item on a list at least once all of these sorts are in here. And that makes sense, right? Like if you have to sort something, there's no way to sort something without at least going through everything once. Even if you're just verifying that it was sorted, that would still involve you going through every single thing in there. So your best case scenario for a sort isn't going to be better than O of n. On the other hand, your worst case scenario for a search is you look through every single thing and it's the last thing you looked for. So you can generally improve on that, which is why your searches tend to be better than that. It's a good one to tuck away. All right, any last questions before I ask you to write me an explanation?
How prevalent is the use of this sort of in the industry as like on a day-to-day basis?
On a day-to-day basis, like not. But on an interview basis, it'll probably come up in like 1 out of 5 interviews. The gap between those two things is well documented. So how that happens is once upon a time when they were interviewing you, they were just checking to see if you paid attention in computer science school. That was the only people they were interviewing. And so they go, cool, did you go to the same classes as me and did you pay attention? Cool, here's how I'm going to find out. What's the big O of a shell sort? Even though, like, I once had an interviewer who was the VP of engineering for a like fairly prominent still enterprise in town. He'd written like a blog series on like how to pass these interviews, and I asked him, I was like, well, why the fuck are you doing these interviews to begin with? Like, you and I both know that like this doesn't have that much to do with like the actual work of it. And he said, if somebody wrote like a quick sort on the job, I'd fire them. It's like, this is done. But I think it's important that we find out that like, do we share a common vocabulary? So like, that's really what that is. So as such, it's becoming less and less common in interviews, but like, this is something you don't want to get pantsed by because it's not a thing you're going to be able to intuit your way through in an interview. And you want to look like you've at least heard of this shit before, and it will come up. So that's the value in this. Like I said, big O in general, that's a great thing to know about because you can go like, God, why does this keep getting slower? Like increasingly slower the more data we throw into it. You probably have an O of n squared happening somewhere.
Do you basically just have to like memorize what the big O's are for different things?
That's probably the best place to start. But once you've worked with these things a little bit, it'll get easier to reason about. And like, this is one of those heuristics that you can use. Is it a sort or a search? All right, well, that helps me put it in one category right off the bat. I go, okay, well, is it worse than N? All right. Is it like crazy worse than N or sort of worse than N? Is it O of N log N? That's still a little bit worse, but it doesn't grow quite as quickly as N squared does. So like, the more you work with these, you'll get faster at it. But to start with, it's probably better to just memorize them. And all of these, like, they have Wikipedia entries, and the big O is listed on all of them. So if I look at quick sort, worst case performance, O of N squared. And the magic of this one is the average performance. That's why people like it so much. Because for most of the sorting algorithms, like the ones you could just sort of figure out, like if you were sorting library books or something like that, most of the average performance on those is O of N squared. The worst case performance on all of them is O of N squared. Oh, this is kind of an interesting thing. So this one has to do with these like pivot points. It's super fucking complicated how quicksort works, but like this is like another one of those things that mathematicians do in their spare time. So a guy publishes this in 1961, and in 1978, a guy figured out the most effective pivot points, which improved the algorithm overall. Other questions? Cool. I would like you to Slack me, each and every one of you. You're at a lame party. Somebody comes up to you, asks you how big O notation works. What are you going to tell them? 3 minutes. Go. Ah, killed my board again. Great answer so far. All right, pencils down. Slack me what you got. Good gravy. All right. So I didn't see a bad answer in the much. So good job all. Doing all right about that. Now let's talk about what one of these algorithms might look like. So this worked okay in my head. I'm gonna see if it actually works that well. Shoot, I think it was designed to go down this low. Fuck.
Ooh, look at that mechanical keyboard.
You goddamn right. Oh man, I was even like, oh, and then the cards, the numbers are on both sides, so we'll both be able to see it. Let me see if I can wedge something in there. Maybe I'll just hold it. All right. So the idea, so let's say I mess up the order of the cards. First, I want you to think, what are all the different ways that you could sort this collection of numbers? Just think to yourself for a sec. How would you do it if I just asked you to put these in order? Think to yourself for a little bit. Any ideas?
It kind of depends if we know how many there are and what. I mean, if we know it starts at 1 and goes to 9, you just look
We
for
don't
1.
know that.
Okay.
That's not a thing that we can take for granted. I just give you a selection. This could be numbers anywhere from 1 to a billion.
You're just asking how we can sort them?
Yep.
Like what way?
How
So
would
you
you
can go-
approach the problem?
Well, depending, I mean, you can go top to bottom to top, evens, odds, any pattern you can imagine pretty much.
Okay, but it's got to be, so to make this an algorithm, it has to be an unambiguous set of steps. So let me show you one. Okay, so I've got these cards here. One on top is 5. So then with my next card is a 4. And I go, cool. Where in this pile does that go? I go, all right, well, it goes there. All right, my next one is a 10. So I look at this pile and I start at 4, and I go to 5, I go, cool. I guess it goes there. So then my next one is a 3. All right, well, that's easy. It goes there. So the unambiguous set of steps part of this is when I go 7, I compare it first to 3, then to 4, then to 5, and then to 10. I go, all right, well, 10's too much. So that means it goes there. All right, my next one is 9. So I go, all right, is it more than 3? Yep. Is it more than 4? Is it more than 5? Is it more than 7? Is it more than 9? No, it's not. That means that's where that goes. All right, 2. All right, well, that's the lowest one. That's easy. It's not bigger than anything. Like, all right, ace is bigger than anything. No, it's not. 8. All right, well, it's bigger than ace. It's bigger than 2, bigger than 3, bigger than 4, bigger than 5, bigger than 7. It's not bigger than 9, though. So that means it goes there. Then 6, bigger than ace, bigger than 2, bigger than 3, bigger than 4, bigger than 5, not bigger than 7. So that means that's where that goes. And now I've sorted the cards. That's called insertion sort. That's you probably do some variant of that anytime somebody asks you to sort something. Questions about insertion sort?
So in the real world, would that be implemented with like a linked list?
Not necessarily. You could. The linked list would be the data structure you would be operating on. The algorithm would still be the same. So the algorithm would be, actually I can show you, I wrote one. Looks like that.
Can't see.
Oh, that's right, because I'm not screen sharing. That's what insertion sort looks like in code. Other questions about insertion sort?
Yeah, can you put it into words other than your example of the cards?
Sure. What I'd say we're doing, let me mess them up again. Is we're building like a second set that we're sorting as we go. So I would say, all right, this is the only thing in the set now, so I know that it's sorted. And then I take, as I go through each new piece, next one is 9. And so I start with this first card and I go, is it bigger than this one? And if it's bigger than that one, I keep going. If there's nothing else, then that's where it goes. If the next one is bigger than it, then that's where it goes. I go, all right, then I take this next card, 10. Is it bigger than 5? Is it bigger than 9? It's bigger than both of them, so it goes at the end. And so like the teensy tiny steps of this is you're going one step at a time, comparing it to the ones that you're actively sorting right now. You're inserting them into the correct place in that, starting at the lowest one and ending at the highest one. Other questions about insertion sort? Cool. Take a couple minutes, do it yourself.
And by do it ourselves, you mean shuffle our cards and sort them?
Shuffle your cards
Okay.
and sort them using insertion sort. Go slow. Try to think of it as a set of steps that you could explain unambiguously to a computer. After you've done it once, do it again. Do it a couple times. Just really drill it into your head.
So with insertion, you're always targeting the lowest number when you're doing the initial comparison.
Yeah. You
You
could do it the other way. That doesn't make it any better or worse, but you just have to pick a side and do the same one each time.
consistently. Okay.
All right. Any revelations or questions from doing insertion sort?
So where does this rank amongst like the fastest methods?
It's like middle. Like it's easy to wrap your head around. It's not especially fast though. But its worst case scenario is the same as quick sort's worst case scenario. Its average case is just as bad as its like like worst case though, which is the problem. Cool. So we got through that pretty quick. So I'm going to show you another sorting algorithm. So this one works the same way. We're going to make another pile. However, big difference here is we look through everything first, trying to find the lowest number. So I go, all right, 5. 5 is my lowest number. Is 9 lower than 5? Nope. Nope. Ooh, ace is lower than 5. Is 2 lower than ace? 3 lower than ace? 7 lower than ace? 8, 6, 4. All right, ace is my lowest card. So I make that the start of my new sorted list. Then I do the exact same thing again. All right, 5 is my lowest card. Is 9 lower than 5? Is 10? 2 is. All right, so 2 is my current lowest. Is 3 lower than 2? Is 7 lower than 2? Is 8 lower than 2? Is 6 lower than 2? Is 4 lower than 2? Nope. 2 is the next lowest card. That means it goes on top of the last one. And you keep going all the way through the deck. That's called selection sort. I am selecting the lowest one, putting it in there. And then I'm selecting the lowest one again, putting it on top. If I keep doing that, I ended up with a sorted list of cards. Questions about how selection sort works?
Why would you ever use it?
You wouldn't. You got better choices. But every computer scientist that you're up against knows how this works, so you should too.
What was this one's called selection. What was the previous one called again?
Insertion. So
Insertion.
before, for each individual card that we got, we were looking at where to insert it in our like ongoing sorted thing. For this one, we are selecting the lowest card and then adding that to the pile each time. Selection versus insertion. Cool. So same as before, take a couple minutes, see if you can do a selection sort. Remember, you're going through and just trying to find the lowest card in the entire thing. You plop it down, rinse and repeat. Try sorting a deck that way. Go. Do I have one that's lower than the card I'm holding right now? All right. Questions about selection?
Why, God, why?
It can be useful to like think about how you would describe something like that in programmery kinds of words. Computers are really good at saying if this number is higher than this number. They're good at swapping things. They're not good at much else. So like figuring out how you would break something down into steps that small, it's a useful exercise. But no, you will probably never write an algorithm like that on the job. Someone's going to ask you about it, though. Another tool that I'm going to give you, might be useful for you, is the sort visualizer. A little bit hypnotic. It's from the TopTal site. So these are all the common sorting algorithms. So this is insertion, this is selection. Bubble's like intentionally a super shitty one. And then all the rest of these are like ones that mathematicians came up with. So this is a visualization of each of these sorts on randomly sorted lists, nearly sorted, so they're also called k-sorted lists. So it's like, yeah, it might be off a little bit, but no individual thing is going to be more than k items away from its actual eventual sorted thing. Something that's completely backwards, and then something where there aren't very many different values. So this is what they all look like. Kind of cool. So our objective, oh, it's gone, was to explain how big O notation works. Everybody knocked it out of the park. And to perform an insertion sort. We also managed to squeeze in a selection sort. What other questions do you have about the world of algorithms?
When I call dot sort, which one's it using?
Good question. Let's look it up.
Can you link that website in chat too?
I posted an inferior video of the same kind of thing, but yes, that's better.
In Firefox, it's merge sort. In V8, it's quick sort. And if the array is small, insertion sort.
So insertion works, am I interpreting that correctly, better on something smaller?
Yeah.
Yeah. No reason to use that big
on
old algorithm.
average, yeah.
Do the search algorithms sort of work in the same way, but instead of like comparing value to another, like you're comparing the search value to your...
Right. So like the one we mentioned at the beginning, you're looking for something in the dictionary. Except you don't have like indexes or anything of like where the letters are or anything. So you open it up in the middle of the dictionary and you go, all right, is it before this page or after this page? And then you cut that in half, and you cut that in half, and you cut that in half, and eventually you get to the thing you're looking for. So it's called a divide and conquer algorithm. That's probably like the simplest search, and most of them work at least kind of like that. Another one is like those of you who've done the DOM. So we like can break our HTML down to a tree of nodes. So you go, all right, I'm trying to find a particular node. That could be because I did query selector. That could be because I have a CSS selector and like the browser engine is trying to figure out like some kind of matching node. So this is called a tree. And if you're searching through a tree, you can either go, cool, is it at this level? All right. Is it at this level? Is it at this level? So we call that breadth first search. You know, this one, or this one, this one, this one, this one, this one, this one. So then there's also a depth first search where you go, all right, I'm going to go down the side. All right, dead end. I'm going to go back up to here. Dead end. It's not there. It's not there. All right, what about over here? Oh, there it is. Found it. It's called a depth first search. And there's, if every node in a tree either has 0 children, 1 children, or 2 children, it's called a binary tree. And there's very specific kinds of like tricks you can use for searching through those. Kind of similar to divide and conquer. But yeah, that's the idea with searches, stuff like that. Other questions? All right, hope you learned lots. Bye.